you very much, Vadim, and yeah, thank you. Oh, I didn't put my mic on. It's okay. Okay. Of the scaling limit. So yeah, thank you. Thank you for the opportunity to be here, and thank you to the organizers for putting it together. And so I'm going to talk to you about the scaling limits of the G beta E characteristic polynomial. So I'm really going to take the characteristic polynomial as it appeared in the previous talk and a couple other times, and I want to give you a probabilistic description of what it is, and it's going to be just for this G beta E characteristic polynomial. I put a couple pictures here. These are simulations of the actual limit process. So it's possible to really create a rule to generate this for different values of beta, and this is at the edge, so you can see there's some sort of non-translation invariance happening. Everything I'm going to say is joint with Gautier-Lambert. Okay, so first of all, this is about the Gaussian-beta-ensemble, and it's appeared a couple of times, but just to remind, for fixed n and for fixed beta, it's a joint distribution on n points, which has this van der Waals structure to the power beta, and it has this Gaussian potential. I'm going to choose my n's and betas so that the eigenvalues will appear between -1 and 1. I'll show a picture of that in a second. That's why there's some funny looking 2's and n's and betas up here. One of the most important structures that we have for dealing with this object in general beta is this Dimitri-Edelman tridiagonal matrix. I've drawn it as an infinite matrix. It's possible to do that, to talk about one random object, an infinite Jacobi matrix. What is it? It has two sets of random variables. Down the diagonal we have normally distributed IID normal 0, 2 random variables. And on the off diagonal we have these chi's, and the only place beta appears is in the degrees of freedom of the chi random variables. The theorem, Dimitri-Edelman theorem, states that, and I've written it in terms of characteristic polynomials. What does it say? It says that if you take a corner out of this matrix, the top n by n corner, the exact distribution of eigenvalues are these. So that's what's written here. I'm going to take pi n, which will be a monic characteristic polynomial, which will be one of the main objects in this talk, which is formed by choosing n, an n by n block. I see I put little n. Yeah, I guess I put little n, so that's little n. This makes sense for all little n. If I take an n by n block out of the corner of this, so take z and subtract a, divide by some scaling, square root 4 n beta. And this is the object with the eigenvalues following this. When little n is capital N. When little n is capital N. Okay. So this is a generalization of classical betas, betas 1, 2, and 4. And I won't make very many connections to classical beta in this talk. So everything will just be through this description, and it holds through general beta. Just to orient ourselves, so in the scaling that I'm doing, the semicircle is going to be on -1, 1. And in this picture, there are known scaling limits for the point processes of eigenvalues, local scaling limits. There's two that you can extract from here, and one is when you look in the bulk, and then you get this sine process. And for beta 1, 2, and 4, as we've heard, it came very early, using determinantal and Pfaffian structure. And then later, in the Gaussian-beta-ensemble, due to Valko and Virag, there was a description by this joint collections of diffusions, which were touched on in the previous talk. And then there's also circular beta-ensemble stuff. I won't say so much about it, but there's a parallel theory, and the local point processes are universal, so you have also the sine beta point process appearing there. There's also an edge theory. So we haven't heard so much about that, and the edge is going to play a bigger role in this talk because it's a big feature about the Gaussian beta-ensemble. And it follows the same sort of picture that in beta 1, 2, and 4 you can take limits of the Pfaffian and determinantal representations and get some kind of description of the point process. There was a sort of limit operator which which will appear later. I'll describe a little bit about this limit operator, which was posed by Edelman and Sutton. And this was then proved there was a convergence proved and some properties of the operator determined by Ramirez, Reiter, and Bureau. There's also another description. There's actually a couple different descriptions here. In some sense, I'm going to give another description, but it's arguable if it's really different. But there's really quite a different description to do Gorin and Shkolnikov also, which comes also by looking at the tridiagonal representation. Okay. So this is basically about point processes and operators. In some sense, there's also operator convergence here. I'm going to talk about characteristic polynomial convergence. And I think it's a fair question, why precisely would you look at characteristic polynomial convergence? For example, if you're trying to show eigenvalue point process convergence, it's not necessarily the easiest way to do it. It's probably unnecessary, and I think it shows in the theory that it was not the way it was done first. But there are reasons you might want to look at the characteristic polynomial itself, and probably one of the most compelling external reasons to look at it is because of conjectures about the Riemann zeta function, which there's multiple senses in which it's been conjectured to connect to random matrix theory, all sorts of ways. This is the one that I'm going to display for you, which is about it's called the stochastic zeta conjecture, or at least that's the name given by these three authors, Shai, Midrasha Mathematicae, and Iqbali. Which is that you take the Riemann zeta function, so this is Riemann zeta, not stochastic zeta, Riemann zeta, and you look on its critical line, and you choose a point which is high up on the critical line. So this number t is going to go to infinity, but you randomize the location, so you inject one piece of randomness, so you're looking at a random point. And then you look in basically a small neighborhood of that random point. Small needs to be understood appropriately, so log t, did I put divide by log t? I did it right. So the points are getting closer, so it's backwards. Okay, maybe it's upside down. You put it on the mean spacing of the zeros of the Riemann zeta function. And then you want to show locally uniform convergence of this to some function. And there's you might try to formulate non-ratio versions of this, but that's much harder. So this has a higher chance of being universal in some sense, and the conjecture is that it really converges to the object which appeared in the previous talk, the stochastic zeta function, and this is at beta is equal to 2. So it's another instance in which beta is equal to 2 has some kind of special importance. There's a lot of other connections I'm not mentioning here. There's types of modeling about how large the zeta function is, which also can be built from random matrix theory predictions. So there's a lot of other work here, and so Keating and Snaith have a lot of work about trying to do that exact modeling, and there's a wonderful conjecture of Fyodorov, Yari, and Keating, which has already come up in this conference in Ofer's talk, which gives an even more precise relationship, effectively, between the zeta values and some sort of characteristic polynomials. Okay, so I sort of went out of order. So this was the stochastic zeta function from the previous talk. It's also a limit of characteristic polynomials. So you can show that it's a ratio limit of the Gaussian characteristic polynomial. So this is work of Shaibi, Hovhannissian, Najmuddin, Iqbali, and Rogers, where they take this very Gaussian polynomial, and so this is the characteristic polynomial that appeared on the previous slide. It's the monic characteristic polynomial. And you take a ratio and you rescale slightly, and it converges to the subject. Okay. Why else would you look at this? So I'm going to pose a sort of broad and a little bit vague conjecture. conjecture, which is that there's another limit you might take of the characteristic polynomial. If the previous one was a type of local limit where you zoomed in around eigenvalue spacing, there's kind of a bulk conjecture also, which is actually the value distribution of the characteristic polynomial should have some nice structure. I don't actually know who to attribute this to, at least in this generality, so please tell me if you know, but basically the conjecture is that if you look at this characteristic polynomial, you raise it to a power alpha, you renormalize by its mean, then this, as a random measure, is going to converge. And it's going to converge to an object which has a lot of universal features. There's some details here which are embedded here. So it's not quite a totally universal object, but it's a Gaussian multiplicative chaos, and I'll say a little bit about it. So I think it's a really nice object. It's kind of, in a sense, one of the nicest constructions of random fractal that you can get. It certainly isn't obvious if looking at the characteristic polynomial why it would come about. Why should you believe such a conjecture? Well, there is some work. And in particular, in beta is equal to 2, there's been a lot of success in establishing this. So really the question is, does it hold for general beta? Right, I think in beta is equal to 2, it's completely closed by this work of, get my scholarship right, I think Claes, Faz, Lambert, Webb do it, and maybe Nicolas Saxman Webb did. Oh, this was the circular case, sorry, they did that. The circular case first, and then on the line, this was Claes, Faz, Lambert, Webb. There is actually some work on beta is equal to 1 and 4, establishing it by Kivime, and but it's really in a small alpha regime, so in quite small alpha, so it's not even up to the L2 phase that it's been done. Okay, but this is one motivating reason to try to look at the characteristic polynomial. Now I think to show you this conjecture and say nothing about GMC is really unfair, so I try to give you a one-slide version of what I see GMC as. It's this. So if you change the covariance structure slightly in the GMC, you get what's called a log normal cascade, which really is the simplest way to build a random fractal. It's built by just a rescaling of random densities. So you would take a density at the first iteration, which is just constant on an interval, and then you would rescale it by some amount. Now this is log normal, so we're going to rescale it by e to the gamma g minus gamma squared over 2. And then you're going to iterate by cutting the interval in half and rescaling each half by independent random variables of mean 1. We're going to use the same distribution at every scale. So this will be another log normal and another log normal. And you proceed this way, cutting and rescaling. And this is the type of picture you'll see for the density after some number of steps. There's a couple of key features to observe. This is a martingale, so if you fix a value and you look at the density, it's a martingale, it's a multiplicative martingale. It's just an exponential of a random walk, so it's going to go to 0. So it's going to go to 0 at any fixed point. But the measure can survive, and that's what ends up happening, provided gamma is small enough. So there's a critical level gamma. If gamma is below that critical level, you can show that this converges to a non-degenerate random measure. It has supported on a set of some Hausdorff dimension that you can calculate. There's also a critical point at which it goes to 0, but you can rescale it again by some logarithmic term to get something. Okay. So, are there any questions so far?
Do you have any simulations of this object by any chance?
At 8 orders of accuracy, just the 8th generation. No, I know. I'm afraid I don't have one to present. Yeah.
Previous slide you said that there is some success to the Midrasha scheme.
Yeah.
What does that mean? It looks like either yes or no.
Yes. Versticky Webb-Wong proved this for alpha less than half the critical point, or this the L2 phase where you have a second moment. But it was then increased to all alphas in the beta is equal to 2 case, for which this condition holds, which is exactly this critical value in the next slide.
Correction for 2 and without the
That's correct, yes. Good point, yes.
So in beta equal to success.
Success, yes, absolutely. Okay. Good. Other question? All right, so
Didn't they need some wave normalization?
Blaise Faz van Herkwen? I don't think so. Okay, I'll just pose one other reason you might want to look at characteristic polynomials for this model, and it's the operator theory of the infinite model. So if you want to establish properties of what this operator does, one way to approach it is by watching in this evolution of characteristic polynomials. The characteristic polynomials have some relation to eigenfunctions or almost eigenfunctions of this A. So you can try to extract spectral information about the infinite operator by developing characteristic polynomial approximations of the finite one. Now, there's a bullet point here, and I put Kilop's question, and I've talked to people about this because I'm trying to source exactly the question. It might actually be Balin's question, it's better. So it's some combination of Kilop, Balin, and the world, which is, in fact, that there's a conjecture for the spectral measure of this operator. And the spectral measure is a measure which is defined, here you can define by moments, as the integral of the kth power of x. And the spectral measure is this kth power of this A taken in the 1, 1 entry. And I might have needed to renormalize this slightly to be correct, but this may or may not have some connection to GMC. So there's two levels of question. Is there a question that relates it to GMC, and what is the answer to that question?
So what is absolutely continuous? The measures here, probability measure and the number measure.
Yeah. Okay. So that's also, yeah. There's two levels of. I just don't know the answers to any of these. So I'm gonna say there's a question here. Yeah.
The question is not very clear.
So I think you could be bold and say, is it a GMC?
Ah.
And then you could have an answer no, and then you'd now make it precise and figure out why it's no. Or maybe the answer is yes.
The question is, I think the question is clear.
Okay.
Can you relate
You have
to
a limit
GMC?
measure, but maybe not the GMC, but it's also on the level for each omnibus. Just, for example, take the GMC, multiply it by some non-Gaussian
So you
function.
think there exists a couple of
Yeah.
Okay.
Okay. Okay, so here's what I'm going to tell you about. So I'm going to tell you about the characteristic polynomial. So my plan is I'm going to introduce to you a transfer matrix recurrence, which is going to give you a description of the characteristic polynomial for any n. This transfer matrix recurrence is going to have three qualitative regimes as you let it evolve. Those three qualitative regimes are going to require three different analyses, and they're roughly going to correspond to where you would look in the plane at the characteristic polynomial. If you're only interested in studying the characteristic polynomial in the bulk, and I have bad news for you, you still have to do all three regimes. There's not a way to avoid it. All three regimes of this recurrence appear in the bulk points of the spectrum. So I'm going to start by the easy part, which is outside. I'm going to come to the edge, where actually most of the work is, and then I'm going to go to the bulk. Okay, what are the three regimes? What is the transfer matrix recurrence? The transfer matrix recurrence, it's just the three-term recurrence for the characteristic polynomials. So you can just arrange it in a certain way. So I'm going to introduce some variables x and y, which take the randomness here and standardize them. So these are going to be mean, zero, variance, one random variables, so that you have a sense of the scales of the objects involved. And then in terms of these x's and y's, I'm going to take a new a scaling of the characteristic polynomial, which is going to be this phi. And I'm going to introduce just a prefactor. It's a deterministic prefactor. It's going to be a Gaussian weight and some n to the 1/4 and a bunch of square root 4 of n over k's. If you're familiar with how Arabic polynomial recurrences go, this is exactly the prefactor you should put in front of an Arabic polynomial to make them orthonormal. Okay, so if you do it, you have a new 3-term recurrence. So this phi n minus 1 can be written this way. And this matrix Tn, this 2 by 2 matrix, is the transfer matrix. Yeah, and so as I said, if you want a justification for these things, if you take the expected characteristic polynomial, then in fact it's exactly the normalization you need to have this nice orthonormality. Okay. If you're looking for a proof of this fact, in fact, this representation is the best. X and Y are independent of these, so if you just take expectations on both sides, what you see is that you get exactly the right recurrence for the oscillator wave functions that satisfy this. Okay, so this is the transfer matrix. I claim there are 3 big sections of how this recurrence behaves, and actually that's determined completely by the mean behavior of this characteristic polynomial. So these 3 regimes of the transfer matrix are also in the Arabic recurrence, the same 3 regimes, and now they're being randomly perturbed. What do they look like? Well, they essentially have to do with the eigenvalues of the expected recurrence. So the expected recurrence is this. If you compute the eigenvalues of this 2 by 2 matrix, it's basically determinant 1. I'm slightly off. You could, if you want, make it determinant 1. And so you have eigenvalues which are either in 3 cases. Either you have real and separated eigenvalues, one is larger than the other one. This is the hyperbolic region. Or the eigenvalues are equal. Now that only happens at exactly 1n, or maybe never. So there's actually going to be a region around this point at which the eigenvalues become equal, where you need to do something. And then you also have complex conjugate pairs. So this transition is continuous. This is not a phase transition. So if you look in an appropriate large window and you have some flexibility about where to draw these lines, you should have overlapping descriptions of this transfer matrix recurrence in all 3 sections. The philosophy of what we're going to try to do is we're going to try to do as good a job here and make this as big as possible to make what happens on either other side easy. You don't have to work as hard there. I drew some cartoons. I don't know if these cartoons are educational or not, but what are these? These are perturbed orbits of a point under the dynamical system of this type. So a hyperbolic transformation of the disk. I'm running it. It sends a point to the boundary, and I perturbed it. The elliptic one is just a rotation, so going around in a circle. And the parabolic one is one of these cyclic things where there's a cycle going along to the boundary tangentially. This will not be really used. I mean, it's important in some level on how we analyze these problems, but I'm not using the geometric picture to execute anything. Okay. These eigenvalues depend on n. So as you evolve n, the turning point will occur. So when you start the recurrence in this setup, you're going to start with this hyperbolic section, and as you run it, the turning point will appear at this nz squared. It can be that z is bigger than 1. If z is 2, this is 4n. And then you never reach this point. That's true. You don't have any turning behavior. You just have hyperbolic stretches. So when z is outside minus 1, 1, you just have this part. So that's what's happening here. All right. If you're right at the edge, so if z is equal to 1, then the turning point appears at the end of the recurrence. And so you're going to see this parabolic section. And if you're in the bulk, then you're going to have an elliptic section. There's also a technicality which is really, I really just want to ignore, but it's hard to, which is that if you're really close to 0, there's yet another thing which is happening, which doesn't quite fit in this picture. So there's an exceptional region when nz squared is bounded. It's not long, it's just a finite number of terms in the recurrence, but it doesn't quite fit into this picture. So there's also an exceptional rate. Okay, so what happens outside the disk? I want to formulate a statement about what you can do with the characteristic polynomial recurrence outside. Well, this is going to be the analysis of the first part, the hyperbolic part of the recurrence. There's a map which is absolutely everywhere in Eremite polynomial asymptotics, which is this J map. What does it do? It sends conformally, it takes C minus the slit, and it maps it to a disk. It maps it by taking these little ellipses and sends them to circles. If you want to describe the characteristic polynomial away from -1, 1, the simplest way is to build a Gaussian analytic function, which is this Gn, which is just the sum of real Gaussians times z to the k over square root k. And I run it up to n. So these are IID normal 0, 1s. And then I'm going to take Wn, which is just the composition of this Gaussian analytic function with this J map. So this thing is behaving well inside the disk. It's log correlated. It's a nice log correlated structure. And then we're going to compose with some kind of chart, which is going to make the formulas all look weird, but otherwise manageable. And what you can show is that in the hyperbolic part of the recurrence, so in the part of the recurrence where the eigenvalues are real and separated, the characteristic polynomial is effectively Gaussian. It's log normal. I mean, is Gaussian, I have to do a coupling for this. I took random variables, I have to couple them on a probability space to Gaussians for this to be a true statement. It can be done. And it can be done in such a way that you have small errors. So if you take this phi n, you divide by the expected phi n, then it's the exponential square root 2 over beta times a Gaussian, minus 1 over beta times that thing squared, and plus an error term. And it's an error term which, if you like, is either small, and that's if you're far away from the edge. So if you separate more from the edge, it gets smaller and smaller. And you can even write a tail bound for how small it is as some kind of e to the minus r 3/2, and that's how far away you are from the edge. So this is the kind of normal airy scaling for a characteristic polynomial. So we go n to the minus 2/3 away from the edge, and then multiply by r. Okay, so out here, it's all Gaussian. It's just all Gaussian. I don't know if anybody is excited about this or not. Probably is what you expected. Far away, and by the way, this is actually very closely related to like CLTs for linear statistics. In fact, formally you can map this whole statement onto CLTs for linear statistics. It's really in content the same thing. The only way in which it's different is that now we're quantifying this error as you get close to the transition point. Okay, so this is what happens in the hyperbolic stretch or outside the spectrum. That's okay. I'm going to say one word about the proof. It's got a very simple heuristic, which is very satisfying. Unfortunately, the paper is not this long. I wish it was. Why is this so simple? So if you have this phi n minus 1, that's a product of transfer matrices down multiplied by the initial condition. These are hyperbolic here, which means they have one eigenvalue much larger than the other one. So these things have a very large direction and a small direction. If you renormalize by the large direction, they're just killing one direction. Furthermore, their eigenvectors are very closely aligned. It's like smoothly varying eigenvectors along the recurrence. If you extract the largest eigenvalues from each of these things, which are going to be random, then effectively this product of transfer matrices is just the product of the leading eigenvalues. Very nice representation. It's the product of the leading eigenvalues, which are independent and random of each other. So you can do any type of log normal approximation you want to this thing. There's a shape of this transfer matrix. It's even possible to write what this is. This is just related to the left eigenvector matrix of Tn and the right eigenvector matrix of T1. Multiply them, that's the only shape difference. Okay. Why does it become hard? It becomes hard because this would be relatively easy if you have a fixed amount of hyperbolicity. So the first eigenvalue was 1 and the second eigenvalue was half. It should just be something like this. but the hyperbolicity dies as you get close to the edge. So you have to work hard, you have to bootstrap and get more hyperbolicity by blocking and stuff like this, then it works. Okay. So, I would like to tell you now about the transition regime. So what happens in the transition regime? All right, so this is in the neighborhood of the turning point, and we're going to have something completely different. I'm not going to use this parabolic picture, I'm going to use something else. And I need to connect something that's appeared a couple of times, which is the stochastic area equation. So the stochastic area equation is a second order differential equation. Second order differential equation with the noise term. So it's two derivatives of phi is t plus lambda of phi plus square root 4 over beta phi lambda, and then this is a white noise. Okay. We need a solution of this equation, and effectively, what's going to occur is that somehow the transfer matrix is going to look extremely close to this equation. It's going to look like a version of this equation with an error term, and we're going to try to put them next to each other and get some kind of comparison between them. To do it, we need a solution of this, which is going to be our candidate. For example, what happens to the stochastic, to the edge of the characteristic polynomial. Now, this is a second order differential equation. If you just ignore the noise, take beta to infinity, it's the area equation. You know a lot about the solutions of the area equation. It's got a unique bounded solution. It's also got an exploding solution. And basically, the same thing persists. We need the bounded solution of this. But it wouldn't quite be enough to just know the bounded solution of this. We also have to know the constant, well, what multiple of bounded solution, because we need to say that the characteristic polynomial is equal to it. So, in effect, we need to determine a way to get the asymptotics as t goes to infinity, I'll explain why t goes to infinity, of a solution, of the bounded solution of this stochastic differential equation. Something nice happens. So there's a unique solution of this equation with the property that as you send t to infinity, it behaves like the deterministic version. So this is just airy. And there's a t plus lambda here, so it just ends up shifting the airy. And then you have essentially some kind of Gaussian multiplicative chaos, which is now some square root 2 over beta. It's an integral of some explicit functional, maybe not particularly intuitive. By the way, that letter is an x. But this letter is an x, and it's a Gaussian process, which is some explicit integral of dw of this white noise, this very same white noise. It's important that it's the same one. If you wanted to have one qualitative feature of it, maybe the important part is that its variance is diverging logarithmically as you go into infinity, and that's consistent with this log correlated field behavior that we see in the exponential, the log of the characteristic polynomial. Okay, so actually, this theorem is that there exists a unique solution of this with this property. One way to say it is that, I mean, the fact that there exists a bounded solution, I don't know if that's particularly hard. The fact that there's a unique bounded solution is maybe also not particularly hard. So the actual extra information here is the asymptotic behavior of that solution as t goes to infinity. Okay. So I want to say how this relates to the picture that I've shown, and I need to say at least one thing about what stochastic area does. And this is also in terms of if you wanted to approximate the stochastic area function, how do you do it? And one thing that you have to know about the solutions of the stochastic area equation is if you just try to run the initial value problem, so that's what I've done here. I took some time, and I let time go to infinity, and I solved that second order SDE. And what you're seeing in this red line, which is just one distinguished solution, is they all go off to infinity. In effect, they're all picking out the exploding solution. That's a statement that will hold with probability 1. You cannot get a solution of the stochastic area equation which is bounded by picking a time and running this forward in time and solving the can if you go backwards in time. So this is the stable direction. So what you should do is you should look at a large positive time, and you have to run the equation backwards, and then you see Airy behavior is generic. That also gives you a way to generate approximate solutions of the stochastic Airy function. What you should do is look at a large positive t, set some initial conditions, and then just run it backwards. We can also tell you then what you need to divide by in order to make that consistent across various t's. Okay, so this is what an approximate solution to the stochastic Airy equation, or how to generate them. And it's interesting to maybe pose some properties of this. I have to say we don't, I think, know very much about the stochastic Airy function. So, you know, if there's some expectation or some interesting property of the stochastic Airy function, it's probably open. There's a few things which I point out, which give it some nice properties. First of all, this is a random entire function in lambda for every t. It is a C1 function in t. So if you differentiate a time, you actually have one classic derivative. You can take a second derivative. That's an ito derivative. It has an invariance in law. So this is exactly the right tail conditions to satisfy the following property, which is that if you shift the spectral parameter up and you shift the time parameter down by the same amount, you get the same function back. So in law, this whole process for complex lambda and real t is the same as shifting spectral up and time down for a fixed amount. In actuality, that's just because the underlying white noise is time invariant. So I'm just taking the time invariance of the white noise and pushing it to what it means for the solution of this ST. The zeros of this function are the Airy point process, the Airy beta point process that we've seen that's appeared so far. You can connect it a little bit more to the stochastic Airy operator. The actual time dependence here allows you to create eigenfunctions of the stochastic Airy operator. So 4 eigenvalues here. If you look at this as a function of time, it is an eigenfunction of this second-order differential operator. I put some contour plots just so you can sort of see that there's this Tx invariance. So that's coming here. This is beta is equal to 2. I don't know if you can see it. This is beta is equal to 0.1. These things are definitely looking more boxy. It's known by work of Lord that if you send beta to 0, that you have some kind of Poisson point process arising. So this looks a little bit like some sort of PNG or some sort of plane diagram of Poisson, which maybe is also true. I don't know. It's just based off this picture, some type of convergence. These are contour lines of that's where it's equal to 0 of the stochastic Airy function. Okay. But basically, we don't have a lot of properties of this function. Just it exists. It has some asymptotics. We don't, for example, know its other tail asymptotics as t goes to minus infinity. We know t goes to plus infinity. T goes to minus infinity. We don't know. We don't know any lambda asymptotics also. Lambda going to infinity. Lambda going to minus infinity. You can get some kind of in-law behavior from this identity, but nothing almost sure. Okay. Why does this appear? Or why does this appear? Well, this it comes right out of the recurrence, and this has been known for a while, and this is the basis of the operator convergence of to the stochastic Airy operator, and why we know that in beta ensembles you see the Airy point process at the edge. If you take the recurrence in a neighborhood at the edge, so we're looking at the z, which is 1 plus lambda over 2n to the 2/3. And you substitute it into this equation, and you rearrange the terms, and what you can see is that you have a discrete Laplacian of psi, and up to some error terms, it's given by something times psi n minus 1, and then I've arranged all the noise terms, x's and y's, times psi n minus 2 and psi n minus 1. So, this is really reproducing the stochastic area equation. So you have some second derivative, approximate second derivative of psi. You have t plus lambda times psi, so this is becoming your t under your lambda. And then here you have some noise, increments of noise. These are all independent in n times psi itself. So what's relatively easy to show is that this characteristic polynomial satisfies, in a formal sense, this equation with an error term which is going to 0. That's been known for a while, and that's the basis of the point process convergence. I think it's worth saying that, okay, so what's different about what I'm doing? So the point process has been known for a while. It's based off of this. What do you have to do to get the characteristic polynomial to also be approximated by the stochastic area function? Well, there's an important part here. The first thing is that this is really in the good direction of time. So I told you earlier that the stochastic area equations are stable, but only running backward in time. That's the direction which is appearing here. So this psi t hat, just remind you, psi t hat is really this renormalized, sorry, I put it here, it's the characteristic polynomial, and then you rescale time to be n times t to the n to the 1/3. So this is really an approximate solution of the stochastic area equation, and if you work out how the time is set up, you have a terminal condition. So you have a terminal condition of large time, and you are running this backwards. So that's good. Now, if you want to compare this to the actual stochastic area function, one approach you can use, the approach we use, is to make an instance of a kernel, a type of solution operator kernel of the second order differential equation, which is just built out of Dirichlet and Neumann solutions of the stochastic area equation. So lambda is the spectral parameter, and these are functions of t and u. The whole point is that we have an approximate solution of the stochastic area equation, and we can represent how close our solution is to the stochastic area equation by integrating some kind of derivative of this expression times the error term that appears in the second order difference equation on the other side. And the error term is small as a function of n. So this is like n to the minus a sixth, and this t is roughly on a compact amount of time. So as long as this thing doesn't do anything wild, the error term between these is actually going to be vanishing as a function of n. But what we have to establish is some kind of boundedness of this. So if you know some kind of boundedness of this stochastic area kernel, the limit object, then you can show that approximate solutions are close to the true solution. And so the whole problem, in a sense, is to get good estimates on this and various regions. So I'll just say a word about it. I don't think I have too much to say here. It's just if you want to control this kernel, the standard method is to, well, we have some kind of need to say things about Dirichlet and Neumann solutions of the second order differential equation. And in the business of second order differential equations, the Riccati transform, so the log derivative of the solutions is very helpful because it satisfies an autonomous first order SDE, first order nonlinear SDE. So this is what it does. So if you take this DDT of a solution of the stochastic area equation, you get some kind of first order equation. It's d rho is t plus lambda minus rho squared dt, and a noise. And I think basically every theorem about stochastic area to date has involved an analysis of this wrong. What we have to do here, which is maybe a little bit unique, is we have to do an analysis which is on compacts of C. So we're doing this as a complex function and not just as a real function. Okay. So I just formulate what we get from all this. So if you look at the edge, so you should think of Z as being close to 1 here, and you're looking at an edge in a region which is about n to the minus 2/3. So we have a little bit fatter region than n to the minus 2/3. We have some log n in one direction and e to the square root log n in the other direction. Okay, then the characteristic polynomial in its edge scaling has a couple of parts. So we have the same log correlated Gaussian field that appears here. So it's an exponential of this same Wn from before. It's actually, there's a small change in the behavior, but it's effectively the same. And then it's multiplied by a stochastic, the solution of the stochastic area, or actually the actual stochastic area function. And in order to execute this, we have to put these on the same probability space. We have to somehow take the noise from the A and compare it to Gaussian noise in order to actually compare this function to this. And the error terms are small in different ways, but okay, it's not important. But the error terms are small with a tiny probability. So this is smaller than any power of n. So if you want any sort of statistic about phi, you may as well be looking at the stochastic area function at the edge. That's the point. All right, so I'll just finish with the final section. I'm not going to go very much into depth. I know this was technical talk, so I'll just say what the result is here. I should say the previous two works are available now. This one is not available now, so it's supposed to be available. So I'll just define the object. This is a different representation of the same entire function that appeared in the previous talk. So this is the stochastic zeta function. I'll introduce it through, it's some SDE. So you have d psi, it's going to be a complex SDE, and lambda will be the scaled spectral parameter. And then there's this interaction term, which is this complex Brownian motion now, and square root 2 over beta times 1 minus e to the I imaginary part of psi. You can define the zeta function, which is the limit of the characteristic polynomial on R, as this. You take this is for t running from 0 to 1, so you run this up to time 1. And then you look at zeta, which is the real part of e to the I alpha plus psi 1. So psi 1 is the solution of this equation. Alpha is a uniform random phase. You have to inject one other piece of randomness, this uniform random phase. And then you take the real part of that, you divide by the real part of e to the I alpha. And it's maybe not obvious, but it is in fact the same function which appeared in the previous talk. Doing what lambda to be? Yeah.
It can be a real value function.
It's not a real value function at all. This is a complex Brownian motion. So this is sort of never real valued.
So your psi is real value. Or is zeta?
Zeta is real value. This is on R. Yeah, absolutely. Sorry. Yeah. Right. Good point. Yes. Yeah. So yeah. Sorry. This is just on R. Yeah. So the zeros of this are the sign process. This is one way to define the sign process. And actually, if you unfold everything that's written here, essentially equivalent to the original way the sine process was defined in terms of a coupled family of diffusions. The sine beta process, of course. And the only additional thing I want to add then is that this thing really is the limit of the characteristic polynomial, of the G beta E characteristic polynomial. So this was known for the C beta E. It's a big block of text, but you can really see it appearing in the G beta E. Let me just say what's on this slide. So first of all, this is just formulated for being away from the edge by some amount, which is going to infinity. And a lot of this is going to be very similar to what you would see if you look at the Hermite function. Very, very similar to what you see if you look at the Hermite function. You would not have this psi, and you would not have these random terms. Well, you would have a deterministic sign, sorry. But these parts are exactly what you see in the Hermite recurrence. So you have some big phase, and this has to do with the integral, the antiderivative of the semicircle. This is the semicircle. You have some correction term. This is formulated at a z, and I divide by this is the semicircle density right here. This is z plus lambda over n times that. So here is the deviation of how lambda enters into this. So this is all a function of z, this is all a function of z, this is where the lambda is. This thing is going to be an approximate solution of the sine equation. That's where that appears. This is a giant non-Gaussian martingale. It's non-Gaussian, maybe this is the most exciting part, this is non-Gaussian precisely because of what happened in the previous section. There's a turning point. So to reach here, you have to go through this non-Gaussian turning point section. You pick up something that looks like the stochastic area function, and it doesn't go away. It's just there. It's part of the martingale. It is a martingale, so it still has lots of good properties. And then you have some kind of error term. So the martingale, this is the bracket. So the bracket, because we have filtration, we can evolve the steps. The martingale coincides with the covariant structure of this W. W was way back when it was the GAF composed with the Joukowsky map. And these parts, this psi is becoming a solution of the stochastic sine equation, the complex sine equation, and this part, if you look at this sort of the mod 2 pi part of this, all this stuff, it'll be uniformly distributed and finally independent of the sine. So from this statement at the bottom, you get ratio convergence to the zeta function. So there's maybe a couple other things to say. So the first thing is that the non-Gaussian parts here, if you're looking at 1z, for example, if you look at your favorite statement about the characteristic polynomial, like Fisher-Hardwick or something like that, the non-Gaussian parts are coming from the turning point section of this, not towards the end. So this martingale is nice and Gaussian at the end of the recurrence. So the stochastic area function is contributing some kind of non-Gaussian term. If you separate x and y by some mesoscopic region, which is going to look weird. So if you take x and y and you separate them by n to the minus a third, right? There's usually nothing interesting happening at n to the minus a third at 2 points in the bulk of a random matrix. Then these turning points don't align at all. So they don't contribute anything to the covariance. And you get that these error terms in the covariance vanish. These really become little o1 terms. This is separated. Don't know what to make of that. And I don't know any other theorem that I can point you to where that n to the minus a third is relevant. So I don't know what to say about that. So that's an open question. Why? Does it matter, or is there some other kind of extra universality here which makes it not matter? I think I have nothing more to say unless it's just this, but I can't really take any questions.
Thank you very much, Elliot. Do you have any questions? Please.
Yes.
So, conjecturally, what one should expect when you go to elliptic? How this one
so this is finally all of this stuff is from the elliptic part, right? So yeah. So this after the turning point, I would quickly. So after the turning point, the elliptic part starts. So we're in the bulk somewhere, and we have a stretch of recurrence, which is of length n, order n, which is elliptic, and which gives rise to, in fact, the whole eigenvalue process is coming from it. Yeah.
So from the stochastic decay process, we move towards what you can recover the sine decay process. Can you recover the stochastic zeta function from your stochastic decay?
Yeah, it's an interesting question. My knee-jerk is no, but I don't know if I can justify it exactly. No, it's a good question. I don't know.
Elliot, I see that lambdas are real here. So how important that is? It hard to extend a little bit complex plane?
Yeah, it's a great question. So I didn't. Yeah. So in a tiny neighborhood of complex plane, potentially it would be a very very thin strip. So maybe, but 1 over n, I think.
So in all your results, you're only on the real axis, right?
Yeah. So in fact, in this area result, we could be in a shrinking neighborhood of the real axis, but it's, where is it? Somewhere. Not this one. Yeah. So this could be in a shrinking neighborhood of the real axis as we prove this. I actually think that probably we're going to just prove this for what we have now is just real. There is a general criterion under which, in law, if you show it converges, then you can upgrade to convergence on compacts because it's in the Laguerre-Fourier class. There's a paper of Asiotis on this. But with error terms, it becomes more complicated.
Okay, then a related question, like if it were complex, then you could upgrade to like derivatives immediately.
Yeah.
Is your topology of convergence now such that you can upgrade to derivatives as well, or is it really without derivatives?
Okay, great question. Also, yes. So also in the stochastic area sense, this we showed uniformly in all derivatives.
Oh, it's uniformly in all derivatives.
This one, where is it? So this theorem is uniformly in derivatives in lambda because we can show slightly complex. This, no, but we can show the resolvent converges on the real line, just because we know enough extra about it that it works. But no, we don't have convergence of derivatives. Yeah.
So all this is about the Gaussian-beta-ensemble, right?
Yeah.
So if I ask about, say, Laguerre, do you think it would just transfer, or is it just because?
Okay, so no, it's a great question. I definitely would be hesitant to jump into doing Laguerre. There's certain things that adapt, I think, quickly. So, for example, the turning point, which is, I think, maybe the hardest extra technical thing that you have to do is, so this area function region. Our analysis really is about the limit object, and because we did the analysis on the limit object, if you have something which is approximately a solution of the stochastic area equation, now pushing that through to get an actual solution of stochastic area, that would be easy now. So for Laguerre, this would be straightforward. But for the elliptic part, there's still a big phase analysis, which is kind of ad hoc, and would be a substantial amount of work to, I think, to still do that for Laguerre. Yeah.
Any other questions? Thank you very much, guys.